Okay, let's look at some of the transformations of a trig function. And these transformations are the same kinds of transformations that you would see for any kind of function. What I have graphed here is just it's y equals the sine of x. And you look here, if you look in this expression window here, I have f of x is equal to a, capital A, times the sine of omega, this w, I'm going to call it omega, times x minus p, and then a plus b at the end. Let's just explain, define what each of these things are. A is the amplitude of a function. It has to do with a vertical stretch. We're multiplying all of the outputs by some number. And so that would be a vertical stretch, but for a trig function, we call it an amplitude. Omega, that's multiplying the inputs of a function by some value, so that would correspond to a horizontal stretch or compression. And then p, we're subtracting from the x value, so that's going to have, or adding, like if p was a negative value, effectively we'd be adding. But either way, what that results in is a horizontal translation, so it's a shift left or right. And for a trig function, we have a special word for that. It's called a phase shift. And then finally, this B, usually we use capital B for this, represents the vertical shift. So how high up or down it shifts, a vertical translation. These are all actually pretty straightforward. And let's just look at a graph and see what these do and see how we can like visualize each of these changes by changing them. So we started off with just basic. If you look at the current values, A and omega are both 1. So this is just effectively it's y equals 1. So forget saying the 1. Y equals sine of x, okay, because omega is also 1. So this is the graph of y equals sine of x. Something really important to note right away is that the period here, the period of y equals sine of x, or when it starts to repeat itself, we see it starts, if we say it starts right here, it goes to there, and then we have, it starts repeating itself again, like it heads up after the 0 at 2 pi. So we can say, something very important we can say about the sine function is that in its basic form, y equals sine of x, the period is 2 pi, and there's a special name for that period. It's called the fundamental period of sine. Now, we can adjust that fundamental period by adjusting omega. We've talked a little bit about this before. Omega is the angular velocity. If I just change that to a different value, like let's say 2, that's a horizontal compression by a factor of 2. And we would expect then that the period now is not 2 pi, but just pi because it's been compressed. It's essentially half as long. Okay, so that is the new period now, and there's a really easy formula to calculate what the period be based on what omega is. It's just the fundamental period divided by omega. So in this case, 2 pi over 2, just pi. Um, so that's what omega does. It just stretches out vertically. Stretches out horizontally or compresses horizontally. Okay, if we have a value of omega that's less than 1, we'll have a horizontal stretch. Okay. Now, if we change the amplitude, all that's gonna do is adjust the height of the curve. It's essentially if you have what's called a midline, which is like the middle of all your information, and you see how high is it from the midline to uh, to to the top or from the midline to the bottom, either one, they're the same. That is the amplitude. So it's the distance from the midline to this top point. So we see here that our top line is at a y value of 2.5 and our midline is at 0. And so that the amplitude would be 2.5, and it is. Okay. You could also, if you can't easily pick the midline off of a graph, if you had the bottom value, so if you knew the y value of a minimum here, that's negative 2.5. The top is positive 2.5, and that represents two amplitudes. So if we wanted to know one amplitude, we just take that difference. So 2.5 minus the negative 2.5, which is 5, divided by 2.5. That's the amplitude. Okay. Then we can also, we can also shift the graph. So we can shift the graph left or right. Actually, let's do shift it up first because that's a little easier to see. If we shift the graph up or down, either way, if we shift the graph up or down, this is the B value here, right? It's shifting what we called before the midline of the graph or the middle of all the data, and it just moved it up or down. So if I adjust that, right, if I go up to 3, it took all the data points and just added 3 to them, all the y value, added 3 to all the y values. So the graph is still the same. Like if I revert this back to the default, right, this is what sine was normally. Let me just remove some of these black lines. Sine normally it had that period of 2 pi, but now everything's just been shifted up by 2.5, which is what I put in there. And it could be, obviously, we can have negative values for this too. So if we shifted it down, it would be the same thing. That's just shifted down 1. But everything was still graphed the same way. It just got shifted down 1 afterwards. And then finally, and this is oftentimes the most confusing, the confusing part is the horizontal shift, the horizontal translation, which is also called the phase shift. Now, the way I've represented it here is that omega has effectively been factored out of the x and the p. Um, this is just one way that you'll see this represented. Sometimes you'll see it as omega x, so you might see it as this sometimes, and that is not, in my opinion, this is less useful for us because that p-value now represents, in order to figure out what the actual phase shift is or how far all the x values changed, we would have to divide that p-value there by omega. And we don't want to do that. So if we have this factored out, effectively we've already divided the p-value by omega. And so when I change this p-value, like if I change it to pi over 2, for example, this starting point will shift over exactly pi over 2 as we would expect it to. Right, so this doesn't give me pi values, but that is pi divided by 4, and then this is pi divided by 2. So I shifted it over pi over 2, and now that green line there represents what the phase shift was. So if we saw the graph, if we're asked to determine the equation of like the sine function that's shown on a graph, and we can look at the the point where it would normally start and say, okay, how far away is that from where we should start? Like how far away is that from the starting point of 0, 0, essentially? That would be the phase shift, and we can write it directly into a function that's set up like this. And so those are really all of the transformations. Like you can go crazy and have all sorts of strange things here. And like it could be shifted up, it could have a very, actually the omega could be a super long number. Like so I could draft, and I'd have this weird graph, and it would seem like there's no way that I could take this information here and work backwards to find this, or vice versa. Like if I had this with all these values in it, could I plot it? You can. It's just a very systematic process, and we'll talk about that.